Hello, everyone. Thank you for joining us. I'm really excited for today's webinar, Modern Data Architectures. This is the sixth presentation in our Evolving to Cloud Native webinar series. The content in each presentation in this series stands alone, but as a whole provides a roadmap to modernizing applications that can take advantage of the full power of cloud computing. Look out for a follow-up email after the presentation with links to the series page where you can view past and future presentations along with the webinar and slides from today. For this presentation, we have Aditya Muvavarapu, our Global Segment Leader for DevOps, and Dr. James Bland, Global Tech Lead for DevOps, who are longtime DevOps practitioners with a ton of experience helping AWS customers modernize their applications. Today, they'll be sharing some of that experience with you with a specific lens on data management and how to prevent silos and dependencies that slow innovation. If you have any questions during the presentation, please feel free to chat them into the Q&A panel. We won't get a chance to answer live Q&A today, but we will review them after the event and respond to them as many as we can. So without further delay, let's go ahead and get started with Aditya.
Thank you, Aranita. Our goal is to deliver business value faster and stay competitive in the market. Modern applications center around separating and decoupling the monolith into smaller functional services or microservices that focus on one thing and do it well. Each microservice often has its own data store and can be deployed and scaled independently. They represent the real world where service boundaries are business boundaries. This also leads to an evolution of the teams by giving them autonomy to architect, develop, deploy, and maintain each microservice. Finally, you end up with the ability to make decisions really quickly because the decision only impacts individual services. Cloud-native microservices then take advantage of the cloud for elasticity, platform, and software services. After all, innovation requires change. You can learn faster by making lots of little changes to drive incremental innovation, rather than waiting to take one giant leap. Modern applications were in a way born out of a necessity to drive and deliver small features to customers faster. While this directly addresses only the application architecture aspect, it now forces other teams to build and execute in a similar manner. In order to continuously deliver features, we need all cross-functional teams to operate as one team. Modern applications are pushing boundaries. Users are connected all the time and demand performance, scale, and availability. Users of today expect microsecond latency, access from mobile and IoT devices, and expect to connect from anywhere they happen to be. So what is cloud native? It's an evolving term. With all the software that's being built, it needs a place to run. And you also have to think about how these pieces fit together and cohesively work as a system. The CNCF definition states, cloud-native technologies empower organizations to build and run scalable applications in modern dynamic environments such as public, private, and hybrid clouds. This definition has to be broadly applied to everyone, and not everyone has same capabilities. We call this the lowest common denominator problem. This is where you try to appeal to a broad group and their capabilities. But in doing so, you also need to limit those capabilities that can be leveraged. At AWS, we go many steps further and have a broad set of capabilities in a family we call serverless. Serverless technologies is more than just Lambda. These are services that remove the heavy lifting associated with running and managing and maintaining servers. This lets you focus on core business logic and quickly adding value. As an organization, we've gone through and addressed the different problems that other organizations have or will have at scale. And the services that you see in our product catalog and our partner catalog is a direct reflection of that. As an example, the AWS SDK have features such as retries, exponential backoffs, circuit breakers, and jitters. What this means for you is that you don't have to think about dealing with lower level issues such as transient failures or back pressures. And the SDK handles this logic for you in a manner that scales really well and doesn't cause additional cascading downstream problems. A few other examples of services that remove the heavy lifting of managing and maintaining services are EKS for managed Kubernetes, EventBridge for a managed event bus, SNS for managed pub subsystems, SQS for queues, Kinesis for streaming, and so on. Will help you make sense of it all when we focus on building what capabilities. We just talked about modern applications and why it's important to take a cloud native approach. But before we go on, I want to share with you something we have developed, which is the Cloud Native Journey Map. The map is your guide to the Cloud Native series, but more importantly, it's a mental model on how organizations typically evolve their cloud native understanding. As an organization or team moves from stage to stage, you're gaining capabilities that make releasing new features and functionality faster, better, and cheaper. Today, we're going to dive a bit deeper into the topic of modern data management. Let's take a look at what's different about a modern application architecturally. Historically, applications were built with monolithic three-tiered web architecture that looks something like this, where we have a data layer that has database servers. We have the business logic run in the application layer, and the presentation layer is hosted by web servers. Some implementations have application layer horizontally scaled, but it's still bottlenecked at the data layer. And here's how we see a modern application architecture. Yes, it does indeed look a lot like a three-tier web architecture, but with some very important differences. The first major difference with this architecture, what we see here is not the entire application. This is not a monolith. We're looking at a single microservice. The other key difference with this architecture that we want to explore today are one, data. How and where you store your data is different in a modern application. In this diagram, we can see multiple data store options. Each database is serving a specific need. It's purpose-built for the task at hand. And data stores are also decoupled. 2, application integration and communication. The way you communicate both within your application as well as between each service is different. We're talking about the different approaches to using messaging, events, and APIs within your business. And lastly, compute. The logic you write is important to differentiate your organization. We're building compute technologies that makes focusing on business logic easier than ever. Our customers run tens, hundreds, or even thousands of microservices, which improve their scalability and fault tolerance. Usually, microservices communicate via a well-defined API, and many customers start the process of refactoring by wrapping their application with an API. I want to go back to the point I made earlier. How and where you store your data is different in a modern application. Each database is serving a specific need. It's purpose-built for the task at hand. Our customers are considering what they're doing with their data and choosing the data store that best fits the purpose. For decades, because the only database choice was a relational database, no matter the shape or function of the data in the application, the data was modeled as relational. Instead of the use case driving the requirements for the database, it was the other way around. The database was driving the data model for the application use case. In a relational database, purpose-built for a normalized schema and to enforce referential integrity in the database. Absolutely, but the key point here is that not all application data models or use cases match the relational model. Developers are building highly distributed and decoupled applications, and AWS enables developers to build these cloud-native applications by using multiple AWS services for scale, performance, and availability. Remember, when we spoke about microservices, one of those core concepts of being a microservice is, of course, that each service needs its own data. But why is this important? There are really two big innovation benefits to following this approach. First, it's easier to change your schema, which is generally a big point of contention with monoliths and shared services. When you can independently own and change your schema, the encapsulation lets you evolve your service without breaking the service contracts. The second important point is that each data store can scale independently, meaning that one service may have a small database and another a very large one. But each service can optimize its scale for performance and cost. On this slide are some examples of purpose-built databases and some common use cases. I won't go through them all, but I do want to highlight that with the AWS Cloud, you get access to all these data stores, which can all be spun up in minutes, allowing you to focus on your application and business logic, and not the heavy lifting associated with running and managing databases. Here I want to highlight one of our customers, Duolingo. Duolingo is the maker of a language learning app. Built for purpose databases, has helped the organization serve over 31 billion items for 80 language courses. The primary data store is DynamoDB, which stores personalization for their customers, Elastic Cache for in-memory access to common words and phrases, and Amazon Aurora to maintain user data. So far, we talked about modern applications and how these modern applications achieve scale and high availability by using purpose-built databases. I want to talk about a specific family of databases called NoSQL. NoSQL stands for not only SQL. NoSQL databases are non-tabular databases and store data differently than relational tables. NoSQL databases come in a variety of types based on their data model. The main types are document, key value, wide column, and graph. They provide flexible schemas and scale easily with large amounts of data and high user load. A couple of examples. Amazon DynamoDB is a key value, fully managed data store, and MongoDB is a document database. Previously, before cloud, we were stuck with a single three-tier application. The database that we had were our relational database management systems. This database was responsible for everything. Just to highlight a few common operations this single database was responsible for. One, as companies start out, the database is responsible for transactional CRUD-based queries like get user or update order status. We call these operations OLTP, or online transaction processing. 2, as the systems grew, our queries grew to match the complexity of the systems we needed. We would join multiple tables and write queries with nested inner joins. And 3, if we needed something simple as a basic key value store with hundreds of thousands of entries, the database had also handled this load. And finally, once the company needs to write reports, the database was also responsible for running long-running analytical style queries, which would impact the available resources on the database while the database was serving customer traffic. This load can lead to downtime, loss of availability, and inefficient resource use, meaning this is not a scalable approach. RDBMS was designed in a time when storage was more expensive compared to compute. So SQL and RDBMS has evolved around normalization where storage is minimized. Replicating and duplicating data was considered as a bad practice. You don't need to think about the access patterns ahead of time. You normalize, reduce redundancy in storage, and query data on the fly, but at the cost of scale. NoSQL, on the other hand, was designed at a time when we focused on OLTP and storage was becoming cheaper. Because storage is cheap, duplicating data is not a bad thing. If you are designing for NoSQL, then you must know your access patterns ahead of time. Access patterns or query patterns define how the users and the systems access the data to satisfy business needs. Using SQL means you don't need to know this access pattern ahead of time. 90% of applications we write are written to support common business processes, which represent OLTP or online transaction processing applications. So it's actually one of the most relevant technologies you can learn as a developer today. When we talk about NoSQL, it's important to understand it's not good for everything. It is good for certain class of applications. Those applications have repeatable access patterns. In case of a relational database, the ad hoc engine gives some flexibility. If I don't understand how I'm going to access data, then it would be very beneficial for me to have an ad hoc query engine. And that's really suitable for OLAP or online analytics processing type workloads. A typical relational model is nicely organized in human readable constructs, tables that are related to categories. The relational database is modeled to reduce storage. We step off into the world of aggregated items, essentially pre-built items. Rather than running queries and joins across tables, these items are written as they will be retrieved. This requires understanding the access patterns and writing the data appropriately. And the benefits here are nearly limitless scale and consistent performance. Right-hand side of the slide, which is denormalized for NoSQL, to access all the information for a product, I simply retrieve a single product record to receive all the information on a specific product. And on the left-hand side, modeled after a SQL table, I have to query for a product, execute joins, inner joins, and potentially make additional queries to retrieve all the information for a specific product. The best advice I can give you is to forget about trying to model your data the way you would in a relational database. Designing for NoSQL is going to feel a bit foreign first. It's going to feel harder than SQL, as you already know how to design schemas and tables in SQL. But RDBMS does not scale like NoSQL, and the benefits you gain can be well worth the additional effort to design and think about your access patterns up front. This process can be hard. You have to forget your experience with relational databases and relational table data mapping. Forget normalization. Replicating and duplicating data is okay. You don't have joins. Forget the idea of one entity type per table. What does this mean? You might have a table that has different types of entities in your entity relationship diagram in the same table. And we make sense of it by querying it in a different way to get different views. An example in NoSQL is you may have a single table where all your data for a user profile is in a single record. So you can return that record and all its associated information with a single query for retrieval. Designing for the cloud means we think differently. You really need to think about your data access patterns. Often when we work with customers who are already using NoSQL, but treating it like a relational database, putting one entity per table, creating joins, and general relational concepts into the application. While this is one way to do it, it's not how NoSQL was designed and won't give you the benefits NoSQL was designed for. So watch out for this type of anti-patterns where we fall back to known patterns and design concepts. To take advantage of NoSQL, you should design around the access patterns to ensure that a single query is returning the data you need without having to join and use relational concepts. When designing for NoSQL, you need to get the following information up front. One, you need to define your entity relationship diagram or ERD. Data is relational, we know that, but we don't have to store it that way. To figure out how you want to access your data, your access pattern. If you can't get this upfront, maybe NoSQL is the wrong approach. 3, design your indices around your access patterns. The reason you need to do this is that we want to optimize our database so we can achieve the consistent single millisecond performance at scale. Here are some typical use cases for NoSQL. Most of these use cases take advantage of the key benefits of using NoSQL, having a flexible schema that allows for changes and experimentation of the application. Built for cloud scale, NoSQL databases can scale nearly infinite without impacting performance. Additionally, data models for NoSQL in JSON are natural for developers as the data is similar to code. The use cases are not limited to what's on the screen, but these are just some examples that take advantage of NoSQL's scale and flexibility as a data store. We just covered NoSQL and the benefits of scale and flexibility. Now let's talk about data democracy. Data democracy does not mean every employee needs to have access to every bit of data that an organization has. Instead, it's an ongoing process of enabling everybody in an organization, irrespective of their technical know-hows, to work with data comfortably, to feel confident talking about it, and as a result, making data-informed decisions and build customer experience powered by data. One of the key issues that data democracy addresses is data silos. A data silo is a repository of data that's controlled by one single department or a unit and isolated from the rest of the organization. Data silos tend to arise naturally in large organizations because departments often have their own goals, priorities, and budgets. But any organization can end up with a data silo if not intentional about addressing it. Some ways to break down data silos and connect data assets include data integration. which usually involves extracting siloed data and loading into a target system or app. Data warehouses and data lakes, which can store large amounts of both structured and unstructured data in a repository. 3, enterprise data management and governance, which should focus on preventing new silos from forming. And 4, culture change, which might consist of instituting a data governance initiative or a change management program. The cost of a data silo depends on the organization, but can impact businesses in terms of finances, productivity, effectiveness, missed opportunity, and lack of trust around data. Here are a few concepts I want to cover. A data warehouse is a central repository of information that can be analyzed to make more informed decisions. Data flows into a data warehouse from transactional systems, relational databases, and other sources, typically on a regular cadence. What stands out for a data warehouse is structured data goes through an ETL process, and afterwards, the data is stored in a data warehouse database. The primary persona of the data warehouse is a business professional. A data lake is a centralized repository that allows you to store all your structured and unstructured data at any scale. You can store your data as is without having to first structure the data and run different types of analytics, from dashboards and visualization to big data processing, real-time analytics, and machine learning to guide better decisions. Some major key differences compared to a data warehouse. A data lake has semi-structured and unstructured data in addition to a data warehouse. Plus, a data lake pulls from multiple data sources and is not limited to a single data source and structure. The primary persona of a data lake are data scientists and data engineers. A data lakehouse brings in the best of both the data warehouse and a data lake, providing reliability and structure present in a data warehouse with scalability and agility of a data lake. Lakehouse combines the flexibility, cost efficiency, and scale of data lakes with the data management and asset transactions of data warehouse, enabling businesses intelligence and machine learning on all data. Lakehouse brings different organizational personas together onto one platform. The persona of a data lakehouse are data scientists, data engineers, data teams, business professionals, and software developers. We just learned about the definitions, but why do you need a lakehouse? Some of the key points are: 1, lack of data agility and model reproducibility makes it challenging to meet the requirements unique to businesses. A lakehouse simplifies the complexity of reporting, risk management, and compliance by securely streamlining the acquisition, processing, and transmission of data. 2, data silos prevent a complete view of customer behavior, opportunities, and the insights needed for personalization at scale. Lakehouses unify a variety of data, enabling personalized experiences that drive opportunity and customer satisfaction. 3, vendor lock-in and disjointed tools hinder the ability to do real-time analytics that drive and democratize smarter business decisions. Lakehouses allow for rapid ingestion of all your data sources at scale to make better investment decisions, quickly detect new fraud patterns, and bring real-time capabilities to risk management practices. And lastly, legacy technologies can't harness customer insights from fast-growing unstructured and alternative data sets, and don't offer open data sharing capabilities. Data lakehouses bring together vast amounts of internal and third-party data to share innovative business solutions, monetize new data products, and deliver advanced analytics capabilities. We just talked about data lake houses and the capabilities that can give your business an edge. Now we're going to shift focus a little and talk about DevOps for databases. To level set, DevOps is a combination of culture, practice, tools that increase an organization's ability to deliver application and services at high velocity. In most DevOps implementations, data is often an afterthought. So let's talk about a few DevOps capabilities for database that can help bring it back into the spotlight. The first capability I want to talk about is CI/CD for database. It is the rapid integration of database schema and logic changes into application development efforts and to provide immediate feedback to developers or on any issues that arise. And database continuous delivery produces releasable database code. In short, incremental cycles. CI/CD for database uses DevOps tools such as Jenkins, CircleCI, AWS Code Pipeline, and layer in database-specific tooling that allow for database changes to follow the same development workflow that software engineers and teams are already familiar with. In this example, Liquibase is layered in to provide lifecycle capabilities for databases. Some of the benefits of using Liquibase include version control database schema changes, branching and merging of database changes, which allow for teams of developers to work simultaneously on database changes, and easy rollback of changes, as well as fix forward. The second capability I want to talk about is backup and disaster recovery. The database is a very critical system for most applications and needs to be very resilient. Organization needs to have a clear process and practice for database backup and disaster recovery. Mature DevOps implementation practice game days and chaos engineering to make sure backup and DR work as expected without causing any downtime. The third capability I want to talk about is test data management. Continuous integration, continuous delivery, and continuous deployment all depend on strong test automation. And for the test automation to be reliable and complete, teams need access to quality and complete data sets. Happy path testing is straightforward and often doesn't require extensive amounts of data. But for continuous integration, continuous delivery, and continuous deployment to work effectively, the tests need to be complete, verifying all scenarios and edge cases, which is not possible unless you have access to production scale data. Of course, keeping regulatory compliance and any other organizational policies in mind. And the last capability is observability. With modern applications being hybrid and distributed, it is important to get visibility into third-party services like email, payments, location services, delivery services, and even data changes to get a complete picture as you're debugging your application. A good example would be debugging a failed order. Was it due to a third-party payment gateway being down or a data schema change? Without complete visibility into a transaction, it is impossible to debug and get to a root cause. So here are the key takeaways we talked about so far. Use cloud-native purpose-built databases. One size does not fit all, and you may be trying to solve a problem that's already solved for you in a purpose-built database. NoSQL does not mean non-relational relationships. Relationships are accessed and modeled differently than SQL. You will need to model data differently in NoSQL. So forget what you know about RDBMS. Think about your access patterns when modeling. NoSQL can be a great fit for online transaction processing, where databases are read, written, and updated frequently. And data democracy. Data lakehouses gives you the flexibility, cost efficiency, and scale of data lakes with the data management and asset transactions of a data warehouse. Plus, lakehouses are designed for most org personas, further democratizing the data. Finally, we talked about DevOps for database, where we highlighted 4 key capabilities you want to build. CI/CD for database changes using tools like Liquibase, backup and DR to make sure you're resilient and applications are built to handle failures. Test data management, which is key to achieving continuous deployment where there is no manual intervention to deploy to production. And finally, observability, where we need metrics, events, logs, and traces across all systems, including databases, for complete root cause analysis when debugging issues.
So at AWS, we've been long believers in enabling builders to use the right tool for the job. And when you choose AWS as a strategic cloud partner, you're provided with choice. AWS Marketplace is a cloud marketplace that makes it easy to find, try, and acquire the tools you need to build cloud native. It has more than 12,000 products from over 2,000 independent software vendors listed in AWS Marketplace, many of which you can try for free, and if you decide to use, will be billed through your AWS account. Throughout this webinar series, we'll introduce you to a number of key tools, a sample of which is shown here in alignment to the cloud native journey. At this stage in your cloud native journey, you'll need 3 components. 1, you need a way to get data out of silos and democratize data for all personas in the company. 2, you need a purpose-built database for OLTP applications that can scale to meet the demand of customers. And 3, you need end-to-end observability for your application and data workloads. Here's an architectural diagram that achieves those 3 components that I just mentioned. We have MongoDB Atlas for purpose-built database for online transaction processing, along with Amazon S3 for object storage, and Amazon Aurora for online analytic processing. To democratize data, the solution uses the Databricks Lakehouse platform that serves the needs of business professionals who need to run reports and business analytics, and data scientists, data engineers, and software engineers looking to run ML workloads and surface business insights. Lastly, we have observability by Elastic to provide that visibility to cloud-native applications that span multiple AZs, multiple regions, multiple accounts, and hybrid clouds. Before we dive deep into the solution, I wanted to briefly talk about Databricks. Databricks enables massive scale data engineering, collaborative data science, full lifecycle machine learning, and business analytics. Databricks Lakehouse platform takes the best of data warehouse and data lakes to enable the enterprise on furthering its mission. The Lakehouse platform is built on an open and reliable data foundation that efficiently handles all data types and applies one common security and governance approach across all your data and cloud platforms. MongoDB is a NoSQL document database. MongoDB Atlas is an integrated suite of cloud-native database services that allow you to address a wide variety of use cases, from transactional to analytical, from search to data visualizations. And lastly, Elastic is the solution historically known for the de facto standard search platform, also known as ELK Stack, which is Elasticsearch, Logstash, and Kibana. Today, Elastic offers 3 solutions: Elastic Security, Elastic Enterprise Search, and Elastic Observability. Elastic offers a SaaS model, a self-managed solution, and hybrid deployments relying on federation concepts to offer hybrid architectures. Now back to the solution. So an engineer would check in a database change, also known as a migration, into a Git repository. The recommended format for Liquibase is XML, as this format is database agnostic. The change triggers a DevOps pipeline that reads in the XML, creates the change set, executes the change, and tests the database changes. If the change passes the test, the change is promoted and the environment database is updated. If a change fails, the database change is rolled back and a notification is sent to the engineer. Because Liquibase maintains a history and a sequence of changes, besides production databases, Liquibase is a good use case for standing up databases for sandbox and temporary environments. The solution for NoSQL purpose-built document database is provided by MongoDB Atlas. MongoDB Atlas is a SaaS solution, and connecting this to your AWS account is pretty straightforward. In this example, an AWS Direct Connect is used to connect an on-premise environment to a MongoDB Atlas cluster. The cluster is distributed to multiple locations to provide scalability and availability. MongoDB takes care of managing and maintaining the infrastructure, and you focus on building the business logic in the application. MongoDB's document model naturally maps to objects in code. It eliminates requirements to use ORMs and breaks down complex interdependencies between developer and DBA teams. You can represent data of any structure. Each document can contain different fields, and the schema can be modified at any time. It's strongly typed for ease of processing with over 20 binary encoded JSON data types. The example on this slide shows the relational model on the left and a document model on the right. Notice that all the information contained on the left side is also on the right side, which highlights the simplicity of having all information contained in a single JSON object. It's also easier to read and reason about, and one doesn't have to understand the complex tabular relationships. Perhaps the most powerful feature of document databases is the ability to nest objects inside of documents. A good rule of thumb for structuring data in MongoDB is to prefer embedding data inside documents opposed to breaking it apart into separate collections. These are, of course, some exceptions, such as needing to store unbounded lists of items or needing to look up objects directly without retrieving a parent document. Note in this example that the name field is a nested object containing both given and family name components, and that the address field stores an array containing multiple addresses. Each address can have different fields in it, which makes it easy to store different types of data. And just because MongoDB is flexible doesn't mean you can't have guardrails. So schema and data can be checked via validators that perform schema validations against updates and insertions. Validators are extremely powerful rule processing to ensure data integrity. MongoDB also provides an extension for Microsoft Visual Studio Code, which lets you work with MongoDB and your data directly within your code environment. You can use MongoDB for Visual Studio Code to explore MongoDB data, prototype queries and run MongoDB commands, and create a shared tiered Atlas cluster using a Terraform template. Some top features of MongoDB Atlas. 1, ad hoc queries for optimized real-time analytics. You might have noticed that earlier we talked about NoSQL for online transaction processing. Well, MongoDB does that as well as online analytics processing. Indexing for better query executions. Mongo indices can be created on demand to accommodate real-time, ever-changing query patterns and application requirements. They can also be declared on any field within any of your documents, including those nested within arrays. 3, replication for better data availability and stability. When your data only resides in a single database, it is exposed to multiple potential points of failure, such as server crash, service interruptions, or even good old hardware failure. Any of these events would make accessing your data nearly impossible. Replication also allows you to sidestep these vulnerabilities by deploying multiple servers for disaster recovery and backup. Horizontal scaling across multiple servers that house the same data means greatly increased data availability and stability. Sharding is the process of splitting larger data sets across multiple distributed collections. This helps the database distribute and better execute queries. Sharding in MongoDB allows for much greater horizontal scalability. 5th, via horizontal scaling features like replication and sharding, MongoDB supports large-scale load balancing. The platform can handle multiple concurrent reads and writes requests for the same data with best-in-class concurrency control and locking protocols that ensure data consistency. There's no need to add an external load balancer. MongoDB ensures that each and every user has a consistent view and quality experience with the data that they need. And lastly, Atlas handles all of the heavy lifting behind database provisioning, maintenance, and upgrades. Select the cluster configuration you want using the UI or API and deploy a new cluster or update an existing cluster in minutes. Security patches and minor version upgrades are automatically applied, and all updates occur in a rolling fashion across your deployment to reduce performance impact to your applications. And if a node happens to go down, Atlas immediately elects a new primary and restores or replaces the offline node to ensure continuous availability. In our solution, the Databricks Lakehouse platform combines the best elements of data lakes and data warehouses to deliver the reliability, strong governance, and performance of data warehouses with an openness, flexibility, and machine learning support of data lakes. This unified approach simplifies your modern data stack by eliminating the data silos that traditionally separate and complicate data engineers, analytics, BI, data science, and machine learning. It's built on open source and open standards to maximize flexibility. And its common approach to data management, security, and governance helps you operate more efficiently and innovate faster. In our solution, Databricks integrates with the data plane in a customer's account for access to MongoDB, Amazon S3, and Amazon Aurora database services. The control plane in the Databricks cloud environment allows for uniform access for different personas in the organization via HTTPS, JDBC, ODBC, and REST APIs. Some key features of Databricks Lakehouse. The Lakehouse architecture takes a decentralized approach to data ownership. Organizations can create many different lakehouses to serve the individual needs of the business groups. Based on their needs, they can store and manage various data, images, video, text, structured tabular data, and related data assets such as machine learning models and associated code to reproduce transformation and insights. The Lakehouse architecture helps organizations manage data as a product by providing different data teams in domain-specific teams complete control over the data lifecycle. The Lakehouse architecture provides an end-to-end data platform for data management, data engineering, analytics, data science, and machine learning with integrations to a broad ecosystem of tools. Adding data management on top of existing data lakes simplifies data access and sharing. Anyone can request access. The governance in a Lakehouse architecture is implemented by a centralized catalog with fine-grained access controls, enabling discovery of data and other artifacts like code and ML models. Organizations can assign different administrators to different parts of the catalog to decentralize control and management of data assets. This approach of a centralized catalog with federated control preserves the independence and agility of the local domain-specific teams while ensuring data assets reuse across these teams and enforcing a common security and governance model. And no solution is complete without end-to-end visibility of your application and data stack. With the complexity of modern environments, tracing issues or performance problems across microservices that extend into other AZs, regions, accounts, and even hybrid clouds is difficult without a tool to aggregate all this information together. Elastic Cloud is a SaaS solution that can be deployed in minutes across supported AWS regions and scales capacity automatically, so you can focus on building features and functionalities versus building and maintaining monitoring tools. There are over 23 out-of-the-box integrations for AWS services that allow logs, metrics, events, and traces to be sent into the Elastic Cloud. Elastic supports cloud-native technologies such as Kubernetes, AWS Lambda, DynamoDB, and many others. MongoDB monitoring is a critical component of all database administration, and tight MongoDB cluster monitoring will show the state of your database. However, due to its complex architecture, monitoring can be a challenging task. With the Elastic Agent, logs and metrics are streamed to Elastic Cloud with full visualizations in Kibana. Elastic Cloud supports integrations with both MongoDB and Databricks for full observability across applications and these data sources. Some key features of Elastic Cloud. 1, get up and running in minutes. This not only includes setup of the Elastic Cloud service, but also ingesting data from your AWS accounts and hybrid accounts. 2, save time on operational overhead and focus on delivering business value by leveraging managed services. Automatically scale up or down and pay only for the resources you use. Third, Elastic applies security best practices to help make sure your deployment is secure from the ground up, including but not limited to OS hardening, network security controls, and encryption for data in motion, as well as data at rest. And fourth, collect telemetry data seamlessly, ingesting all business and operational data, including support for open instrumentation standards and open source projects such as OpenTelemetry, Jaeger, and Prometheus. This allows you to consolidate monitoring tools and efficiently store data at affordable cost to visualize and analyze historical trends. To recap our solution, 1, we use Liquibase to manage database migrations and treat data as part of a DevOps lifecycle. 2, we leverage the capabilities of MongoDB for NoSQL document storage that can scale to handle performance and availability requirements of the most demanding cloud-native applications. 3, we use Databricks Lakehouse platform to break down data silos and put information into the hand of all practitioners. And 4, we use Elastic Cloud Observability to bring together metrics, events, logs, and traces into one place to visualize and turn data into actions. The last point is that all these services are SaaS offerings on AWS to abstract away the heavy lifting of managing and maintaining servers and infrastructure. Databricks Lakehouse, MongoDB Atlas, and Elastic Cloud can be used together along with AWS to build the foundation for establishing a well-engineered approach to modern data architecture, and establishing these capabilities can provide a strong foundation for continuing to advance through your cloud-native journey. You can visit the AWS Marketplace website to find and get started with all the tools we've reviewed today. So with that said, why would you want to use AWS Marketplace as your single destination for acquiring third-party software? Research has found that customers using AWS Marketplace are experiencing an average time saving of 49% when needing to find, buy, and deploy a third-party solution. And some of the highest rated benefits of using the Marketplace is cloud readiness of the solution, time to value, and ROI. Part of the reason for this is that AWS Marketplace is supported by a team of solution architects, security experts, product specialists, and other humans to help you connect with the software and resources you need to succeed with your applications running in AWS. You can visit aws.amazon.com/marketplace to find, try, and buy software with flexible pricing and multiple deployment options to support your use cases. And the final takeaways and information I'd like to leave you with today are: 1, visit the Marketplace website to learn more about DevOps and cloud-native tools to support your AWS applications. 2, visit the series overview page to view all the topics we're going to cover in this series and subscribe to updates. And finally, continue your journey to cloud native by registering now for the next webinar.
Thank you, James and Aditya, for that great presentation. I'd like to thank everyone who took the time to register and attend today. We hope you took away some insights that will help you with your current projects. As you close the event, you'll see a link to do a quick survey to let us know what you thought of the event. We really appreciate any feedback from you that we can use to improve future presentations. Have a great day, and we'll see you on the next webinar. Goodbye.